shear flow in closed section beams. So far we have studied shear flow in open section beams for thin wall sections and for open section with booms, etc. Now let us learn how to determine the shear flow values for closed section beams and how to plot the shear flow distribution. Now this is a closed section and let it be subjected to Sx and Sy shear force in x and y direction, and we have obtained this expression in the shear flow in open sections chapter, and you could see here, and we have observed that in the open sections the shear flow at the open end would be 0, so that's why we have taken this qs not to be 0. So qs is equal to the remaining expression holds good for the open sections to calculate the shear flow. Now this is a closed section. If you make a cut anywhere along the periphery of the thin walled closed section, means the shear flow is an unknown value. Let that qs naught be the unknown value we have taken here. Now this expression is valid for a closed section to determine the shear flow values. So qs naught is the unknown shear flow value. So qs is equal to, we can write the expression like this, okay. So this first term is applicable for, or we are very well using for the open section to calculate the shear flow, plus qs naught, where qs naught is the unknown shear flow value. So let this term be q suffix b, qb, basic shear flow or open section shear flow, plus qs naught is equal to qs. So here qs is the final shear flow value for the closed section beam, for the closed section beam. Now let us do the problem. Here a rectangular tube or a thin walled closed section of rectangular shape is given of size 10 inch by 20 inch, which is subjected to external shear load 100 pound acting upward in vertical y direction, and corresponding thickness 0.1 inch, 0.05 inch, 0.05 inch, 0.05 inch. So the given section is symmetric about x-axis. Okay, symmetric about x-axis, and the load is acting only in y direction. So Sx is 0. Since it is symmetric, Ixy could be 0. So when you just substitute, you will get the shear flow expression to be okay. Just I'm talking about the basic shear flow. Okay. So the final shear flow will be Qs is equal to Qb plus Qs naught. Since I'm going to make a cut here, I'm going to make a cut here. Now I'm going to use the basic shear flow expression. Qb is equal to minus Sy by Ix integral Ty ds. Integral Ty ds. Now I'm going to make a cut at O point where the shear flow is 0 and Qs naught is the unknown shear flow. Now let us calculate, once we make a cut, the closed section becomes the open section. Now we need to determine, or we need to follow the same procedure that we followed for open section to determine the shear flow values. So now this is the reduced expression, Ixy is 0, Sx is 0. So the only thing we have to find out is Ixx, the moment of inertia about x-axis. Now you can see here 0.1 b dq by 12, b dq by 12 plus b dq by 12, that is 0.1 plus 0.05, 0.15 into dq by 12, 10 cube by 12 plus this term b d cube by 12, 20 into 0.05 cube, that is thickness cube. So we can neglect the higher powers of thickness like t square, t cube, everything can be neglected. So neglecting that term plus area 20 into 0.05 into distance square is 5 square. So on either side of the axis we are having same thickness, and located at the same distance I can multiply by 2. So after simplification we get 62.5 inch power 4, which is nothing but Ixx. Now Sy is 100 pound, Ixx 62.5. Substitute here, you get the basic shear for QB is equal to minus 1.6 integration Ty ds. Ty ds. Okay. Now, for example, we have made a cut here. Okay. Now this is the shear flow, valid shear flow expression for open section to determine the shear flow values at various different points or locations. Now 0 to A. or O to A, for example, O to A. Okay, so let me consider a small element, for example, here. Okay, so let me consider a small element. Okay, so this is located at a distance s, located at a distance s, and this thickness is ds. This thickness is ds. Okay, this element thickness is ds. So q0 to a, sorry, qo to a, qo to a is equal to minus 1.6 minus 1.6 integration, thickness is zero point 0.1, y distance is s is the y distance into ds. Okay, so if you integrate s, I'll get s square by 2. I'll get s square by 2. At O, s is 0. The shear flow is 0. You can see here shear flow is 0. At A, s is equal to 5. Substitute here 5. You get QA is equal to minus 2 pound per inch. Okay, which is here s power is, you're getting square term. So you get a parabola between O to A. It's a parabolic variation. At A, the shear flow is minus 2. So since I get negative sign, which means that our shear flow direction will be in a direction opposite to the direction of S, opposite to the direction of S. You can see here, opposite to the direction of S. This is the S direction, and this is the shear flow direction after determining the numerical value. So now at A we have got the value. Then A to B, how to find for A to B? Similarly here also at A to B, how will you write A to B expression? You can write here A to B, the shear flow formula, plus the previous shear flow value minus 2. So A to B, so A to B, so we take a small element, here. For example, it will be like this, small element of thickness ds, which is located at a distance s, at a distance s from A, from A. Okay, now this is the shear flow expression. Okay, and we have taken here the element y distance is 5. Y distance is 5. Okay, y distance is 5. Thickness is 0.05. Thickness is 0.05. So integration of ds is nothing but s. Integration of ds is nothing but s minus 2. So now at A S is 0. S is 0. What will happen when you substitute S is equal to 0? You will get the shear flow at A is to be minus 2, which confirms the previous value. So our expression is correct. Then at B S is equal to 20. S is equal to 20. Substitute here 20. You get the shear flow at B to be minus 10 pound per inch, minus 10 pound per inch. So minus, so the shear flow takes the direction opposite to the s direction, opposite to the s direction. Now bo dash, bo dash. Okay, so now so bo dash, now we have to take a small element. Okay, small element, for example, small element. Okay, so ds is the thickness at a distance s, at a distance s from B, at a distance s from B. So now this is our y distance. This is the y distance. So y distance for this element for BO dash will be 5 minus s. 5 minus s. So B to O dash, okay, B to O dash, okay, the previous shear flow, then add this previous shear flow value, and this is the expression for this section. And BO dash thickness is 0.05 for BO dash, and y value is 5 minus s into ds. If you integrate 5s minus s square by 2, at B s is 0, I get minus 10, which validates the previous value, and the expression is correct. Q O dash, so at O dash s is equal to 5. Substitute s is equal to 5, I get minus 11 pound per inch. Okay, you get square term, so you get a parabola. You get a parabola. And we can observe by seeing this figure itself, when the section is symmetric about x-axis and subjected to sy alone, whatever values you get shear flow values on the top of the x-axis will be a mirror image of those below the x-axis also. Okay, you can see here. Now B to O dash is over. Now O dash to C, O dash to C, O dash to C. Similarly, take a small element, okay, small element of thickness ds. This thickness is ds, located at a distance s from O dash, okay. So now y will be minus s, for O dash to c, So now O dash to c, O dash to c is a expression for shear flow, and this is the previous shear flow value, okay. And y is nothing but minus s. Integrate, you will get a square by 2. O dash to c, you get a square term, so you get a parabola. At O dash s is 0, which conforms to the previous value. At c s is equal to 5, substitute here, you get this minus 10, which checks the previous value. Okay, minus, so the direction of the shear flow will be in a direction opposite to the s direction. Now CD, similarly for CD, how will you write? So small element, okay, we take a small element of ds, which is located at a distance s from C, okay, s from C. So now C to D. So as we have taken here, the y distance will be minus 5. Y distance will be minus 5. Okay, C to D. Y is nothing but minus 5. Integrate, I will get S. So straight line variation. Okay. So at C, S is 0. Substitute here. You get minus 10 pound per inch. At D, S is equal to 20. So if you substitute, QD will be minus 2 pound per inch. Okay. So which checks the previous shear flow value at QA. Okay, QA minus. So shear flow direction will be opposite to S direction. Okay. Now CD is over. The D to O. Okay. D to O. So D to O. So we take similarly here small element ds. So at a distance s from D, So this distance is nothing but 5 minus s, 5 minus s, and it is located below x-axis. So minus of 5 minus s, So do, okay, here. So y is nothing but minus of 5 minus s. So minus into minus plus you get here 5 minus s, the previous shear flow value 2 minus 2. Okay, after integration you're getting this value. Then at D, s is equal to 0. Substitute, you get the shear flow, which confirms our expression is right. And at O, s is equal to 5. Q naught is 0, which confirms again. This is open end. Okay, so mathematically we are checking it. Now, how to find out the shear force? Q O to A and Q O to D or D to O, whatever it is. Okay, how to find the shear force? This capital letter Q is nothing but shear force. So the area of the shear flow diagram gives you the shear force 1 by 3 into 2 into 5. So this OA and OD both are having the same shear flow diagram, same shear force acting downward. Then AB and CD having the same shear flow diagram, that is rectangle area plus triangle area, shear force of 120 pound, and BC is rectangle area plus parabolic area. So you find out this, and 106.67 pound is the shear force acting on BC or CB upward. Now we have made a cut, then we have calculated or determined the shear flow values for the open section. Okay, now we have to determine the unbalanced moment which was caused due to this cut. How to find this unbalanced moment? Let us take a moment. About D. So this shear flow or shear force and this shear force will not come into the moment equation as it coincides, and the 100 pound is acting through this through this A, that is OA or DOA, and this will not produce or come into the moment equation. Now this shear force AB, just nothing but 120 acting anti-clockwise, 120 into 10 minus, and this QBC 106.67 anti-clockwise minus into 20. So this is unbalanced moment. Now I want to balance this unbalanced moment to find out the QS naught or Q naught, whatever it is. So how to balance this? We have to add the same magnitude with opposite sign. That value you have to substitute here to find out Q naught. So if you get minus value, same value with opposite sign substitute here, divided by 2A is the enclosed area, 10 into 2, you get this 8.33 pound per inch, which is nothing but Q naught or QS naught. Now you add this Q naught or QS naught, 8.33 pound per inch, with those individual shear flow values which we have determined here. Okay, Q naught, QD, then QC, QO dash, and QB and QA everywhere. See, here you are getting 0 means you have to add that 0 plus you are getting 0. So 0 plus 8.33 means 8.33 will be the shear flow here. And here I'm getting minus 2. So minus 2 plus 8.33 will be plus 6.33 plus 6.33 plus 6.33. Here minus 10 plus 8.33 means so minus 1.67. Here also minus 1.67. So here we will get minus 11 plus 8.33 to minus 2.67 like that. So you can see here. This is the final shear flow distribution for a given closed section. Thank you.